Yes. Yeah. A minute, I will just introduce you. Good evening to all the participants. Welcome to the last day of online session of this AICT Atal FTP on sustainable construction issues, challenges, and technological development in decarbonization. Here we have with us the fifth resource person, Dr. Surajit Debnath, who is head Department of Lab Technology. Let me introduce Dr. Surajit Debnath. Dr. Debnath currently is head of Department of Medical Laboratory Technology, Women's Polytechnic, AICTE, Tripura. He has more than 13 years of experience in medical research, in biomedical research and high-level teaching. Dr. Debnath participated in various academic work in institutions of Germany, Denmark, and Hong Kong, besides in premier Indian labs such as AIIMS, IIT Kharagpur, IIT Guwahati, NBPGR. Dr. Debnath is the recipient of Young Scientist Award from different categories like DBT, DST, and CSIR. A recipient of Tata Trust grant for CME course in Royal College of Pathologists, London. A reviewer of several Scopus SCI indexed journals published by elsewhere, Springer Biomed Central. Along with regular academic activities, he is also engaged with several biotechnology companies in northern and western India as a consultant. He have conducted various workshops and talks, acted as session chairs in international conferences sponsored by national and international academic agencies. He delivered numerous invited talks in national and international academic gatherings. Currently, he is guiding a group of international students for their internship from Russia, Turkey, and Western African countries. Dr. Debnath filed 2 patents in 2021 in India on biotechnology. With this, I welcome Dr. Debnath, Surajit Debnath, for this workshop. Thank you, sir, for accepting our invitation and giving us giving your interest in presenting as a resource. Over to you, sir.
Yeah, thank you. Yes. Thank you, sir, for the organizers. First of all, I should thank you for organizing such an insightful topic, that is sustainable construction issues and challenges and technological development in decarbonization. So what exactly happens is, as we all understand, today's scenarios are a bit different from the classical scenario we had when we were in our we were having our academic regular activities and all. So today, during the pandemic, it was very much evident that the collaboration between more than one specific domains are needed for large scale, what you call, innovation and things that is needed for today's challenges. In this aspect, I will be sharing my some of my thoughts. Okay, so the script. Okay, fine. So just hold on. So okay. So coordinator sir, just let me know once whether this thing is.
Sir, it's visible.
Just a second. Okay. So here what happens, So coordinator sir, whether the screen
visible.
is visible?
Visible.
Okay. So in today's discussion, what I'll try is to give some interactive insight on how interdisciplinary activities would help in the long run. Okay, and it's very much this thing also relevant also to the challenges of today, where we are desperately looking for sustainable practices in most of the domains. Okay, for example, civil engineers will look for sustainable practices in construction and associated activities. Similarly, computer scientists will do the needful in their respective domains. So what exactly happens is, my interest is basically on municipal sewage treatment and how it impacts these current challenges that we are having. As all of you would appreciate that food, water and energy securities are the emerging as increasingly important and vital issues for India and the world. So what does it mean? It means that there is a desperate need of this natural resources for overall development for the country and the whole world. But the problem here is these particular resources are limited. Okay, there is no unlimited supply in this. So what exactly happens is, as countries develop, as cities develop, as a small building develops in terms of various kinds of production, so what exactly happens is consumption also increases. Okay. Now the problem here is, once a resource is being consumed, it emits some byproducts of it, most of which are not usable. For example, wastewater. Let us see this scenario first. Now this is a CWC data of 2020. It's a bit old data, but it shows an excellent picture. Now what is the picture? It shows that in India, this is the India's scenario, and this particular report was submitted to United Nations on behalf of Indian organizations which look after this kind of topics. So what exactly happens is, in India, the need of water is maximum in irrigation. Now subsequently comes the drinking water, industry, energy and other aspects. So it's a clear, it's a statistical study where it has been shown that by 2025, there will be rapid increase in all these sectors. Okay. And if we look at the data of 2050, this is an extrapolation, it also shows a huge demand in all these aspects, these 5 things: irrigation, drinking water, industry, energy and others. You can see one more thing, that in energy, there is a very rapid increase in coming years. Now, the problem here is, India's share of water resources are limited. Let it be groundwater or surface water, whatever. Now, what would happen if all the resources are being consumed rapidly? So, what would happen? The demand should be minimized in order to make it sustainable. And one more thing that can be done is to revamp whatever is wasted. So, the main goal here today is to recharge the wastewater, that is treating the wastewater very rapidly in such a pace that whatever we are wasting, it gets regenerated, okay, with a net zero result. Now this net zero is not possible. Why not possible? We'll come to that. Now this is one more snippet which again shows from the same report to the United Nations from India. What it shows that there are 2 scenarios. One in bigger cities, let us say metro cities, and the second picture is for smaller cities, let us say my city, which is much smaller than Bangalore or whatever bigger cities of India. Now in bigger cities, what is the scenario? The wastewater that is being produced, the sewage that is being produced is huge, and comparatively the blue part, the blue thing in the pie is the amount of water that is getting treated. Okay. Now in bigger cities, the scenario is a little bit better, and in smaller cities, the scenario is much worse. As you can see, the red is much big in the pie, and the blue part is very, very small. So what does it mean? It means that there is a huge gap. Now one more interesting thing is there. You would say, you must have seen that no private player or no private is interested in wastewater treatment or municipal sewage water treatment. All these years, now new startups are being developed and they are trying to do some, they are trying to contribute. But basically, it is not a very profitable business till now, and therefore it has always remained a welfare thing from the government. Okay. But there is one more possibility. What would happen if all our cities reaches a point where it doesn't produce any waste at all? Okay. Now here comes sustainable development at its best, which is very difficult to reach. Okay. It is difficult to reach, but there is no harm if we discuss the possibilities. Okay. So we'll look into this, that how a particular building can produce zero waste. So in the first part of my discussion, I will be giving you some idea that why exactly the sustainable practices are needed. Why Dr. Asif has proposed this particular topic. This is the fundamental question. Okay. Now subsequently we will move on to something that is this possible to make a net zero consumption economy. Okay. Or are there any used cases? Used cases means the established thing which has been reported scientifically, even it is being viable economically. तो ये सही में होता है क्या, ऐसा हो सकता है क्या? That also we'll discuss, and we'll also discuss what are the problems which we'll face in coming days and how interdisciplinary research can help in this particular domain. Okay, so this is the general objective of wastewater management. Okay, so I'm interested in this particular thing where I collaborate with civil engineers like you all, the participants as well as the other dignitaries, and we try to incorporate some of our knowledge so that there is a holistic kind of like innovation. Okay, there is a long-term goal. Now, what are the general objectives of wastewater management? First one is protecting public health and environment, because what would happen? All pollutions will be there, and number of pollutants. Okay, biotic, abiotic, different kinds of factors, biotic factors and abiotic factors both. Subsequently, one more this thing is the meeting the increasing demand. Okay, so what would happen? We are producing a certain quanta of wastewater, and we are trying to recycle that waste so that the increased demand can be met. Okay. Now, third one is reducing the pressure on the scarce water resource. Okay, now that thing is very holistic. In the last part, what we try to say, if you are when you are taking your bath, you try to put only one bucket instead of two buckets. It is something like that, which is very difficult to practice in countries like India. So what the option we are having? Meeting the increase in the demand. So how we cannot produce n amount of water, isn't it? Usable water. So one choice is left, that is whatever is getting waste, we have to recycle it. Okay. Now, what are the innovation? Okay. Now, this particular snippet, if you can see. Now, this is the usual procedure of municipal waste, wastewater treatment. In any municipality you go, these are the steps. By seeing the graphics only, you will, since all of you are already accustomed, this is a very complicated process. Very complicated, time consuming. It takes a lot of energy, skill, and investment, and also it is also not profitable anymore. So in this regard, what will happen? So what exactly happens is, as you can see here, first there will be a primary settling tank. Subsequently, it will move into anaerobic, then aerobic, then anaerobic. All these kinds of which takes a lot of time. You need to invest a lot in your electrical setup, plumbing, and all such things. Okay. So ultimately, at the end of the day, it is not profitable. Okay. But we have no other option. Now, the second snippet is one more method of wastewater treatment in municipal setup. This also gives you the same story, where it seems that it's difficult to achieve, and there are multiple steps involved in it, and it is not yet optimized to the fullest. So what would happen? You will get the end product, but its value is, the whole system is not very much what you call efficient or economically viable. Okay, so there is a lot of room for doing a lot of innovation in this regard. Okay, now this is a simple snippet which indicates what is the cost, what is the overall economy of this kind of setup. Okay, so you have multiple different types of costs. There are three these things: primary treatment, then primary plus ultrafiltration system, and then primary ultrafiltration as well as reverse osmosis. Okay. So in all this, so that you reach a stage where the wastewater is getting completely revamped into completely usable, potable and drinkable water. Okay. So in that, what are the different costs? Capital costs are there, annualized capital costs are also there, operational maintenance costs are there, annual burden of various recurring costs are there. Then there are different treatment costs. Okay. So this particular snippet try to indicate that there are huge investments that is needed. Okay. But in short term, in long term, there is huge impact. There is no doubt about it. But in short term, this thing do not seem viable. Okay. So most of the water treatment or shall I say water bottling companies, what they do, they take groundwater and then do reverse osmosis, and if they add some minerals, that is okay. Other than that, they do the business. Okay, they are not what you call using wastewater as their source material. Now, what would happen? Who will treat the waste? And is there a possibility that we convert the waste into wealth? Okay. Now, this particular concept is also very important. So, what are the use cases? We'll see now. So, these are nothing but the byproduct of increased urbanization and industrialization. If you want to develop economically by putting industries and by putting cities and buildings, so these are the end product. That there will be some kind of waste. Okay, but we will come to a point where we cannot able to do away with the waste. Okay, we have no choice. We will be left with no choice other than completely what do you call recycling the waste, and to produce all our and to meet all our needs from the recycled waste itself. So what are the bottlenecks, technical bottlenecks to reach at that point? That also we will discuss. And what are the use case scenarios? Is this possible at all or not? That also we will discuss. Okay. Now before going to do that, we will also have a little demonstration which will just to make it little more fun, and it will help us to understand that what is the impact of industrialization. Okay. So in this simulation tool, since the time is very limited, what we have done is we have produced a video, and this video when it will run, we will able to understand the differences between the greenhouse gases produced by an industrial nation, industrially advanced nation, in comparison to a less industrialized nation. And the tool works on real-time data. Real-time data means the data is being curated every day. Okay, so that is a centralized server which is being fed with the real-time data from all the countries. Now the problem here is the data is from European Union. Okay, they do have a server like this, which in which they will add the data of which kind of waste and how much of waste they are generating. Now, one more problem in this tool is it doesn't give you it doesn't discuss about wastewater. It discusses about greenhouse gases and most of the air pollutants. Now, in this particular regard, I would like to this thing that it has been already seen that the amount of municipal wastewater produced, there is a high correlation between how much of greenhouse gas you produce. Are you getting? So, this tool will give us an idea that which country is more industrial and what is the impact of industrialization. It will also give us an indirect idea that how much wastewater the country might have been produced. So I have found no other tool other than this which gives us a real-time data, not old data like CWs. Okay. So coordinator sir, I will request you to please share your screen and play the first simulation link that I have sent to your. You can even share it with our participants if they want. Can also this thing. one of my student has made this video. So please share your screen, sir.
One minute.
Yes. So it is just to make the whole thing a little more fun, so that we will able to understand in real time what is the scenario. We have taken the case of the European Union, but we are very much sure that it will be the same for Asia also. Okay. Now in European EU, the benefit is they will give the real time data every month or every week to a central server, which gives us an idea that how much greenhouse gas a particular country is producing and in which way they are producing that greenhouse gas. Okay, it will also give us an idea that what are the different types of greenhouse gases it is producing. Okay, so it may not sound relevant to the wastewater treatment, but it is highly correlated to the amount of wastewater this particular country is generating. So it will give us an idea that what is the cost of development, what is the cost of urbanization. Okay.
I'm trying to share. Is it visible? Anybody?
Yes.
Is it visible? Shall I
can
play?
Make it full screen?
Sir, it is visible,
yes.
sir.
Play, sir. Yes. Okay. So, as I have said, our students are there who run this analysis and all. Okay. Now, this is the tool. Okay. In this tool, as you can see, okay. You can play with the sound, sir.
Yeah.
The sound is not coming.
It's there.
The participants, please have a look, and later on we will also do a little discussion about it. If the sound is not audible clearly, the sound was bit this thing now.
I was playing in the desktop. Shall I play it in my mobile? Second.
Yes. No. Second one not needed right now. In the participants said they had some problem by hearing. The sound was not clear from my end. From your end also it was like this. If it is like this, I'll
Shall I play once?
Okay. Please, please. Then you mute the sound. Yes. You please play it in the full screen and then mute the sound. So participants who are still there, I just want to tell you, in this August gathering, that what exactly happens is European Union nations are such that they will give all the data regarding air pollution. Okay, which kind of greenhouse gas? This is mainly because of the climate change scenario that is being there. Now they are mainly this thing on global warming. Okay, so they are not looking at wastewater production and its what do you call outcome as such, but they are more interested in reducing the temperature increase. That is to reduce the global warming to a significant extent. Now it has been proven that global warming is mainly due to the greenhouse gases, isn't it? So in that regard, they have gathered together and they have made a protocol in which they have agreed to feed the real-time data every week to a centralized server. Now this is the server. Now what we exactly did is we have used a comparative analysis between two countries. One, Great Britain, which is industrialized. Like Great Britain, Germany, and all such countries in European Union are much more industrialized compared to the Scandinavian countries. Let us say this thing, what do you call this particular thing, like Iceland. Okay, is much less this thing, what do you call is industrialized. So what exactly happens here is, okay, now what exactly happens here is by seeing the data itself. Now this is the Great Britain data. Okay, it will come. Sir, you can even share the link to the group also, means the chat box also, if at all some participants want to go through it, if at all, so they'll just give it a click and they can answer. Okay, so what exactly happens here is it clearly shows that the maximum amount of greenhouse gas, whatever kind, sulfur dioxide, methane, carbon dioxide, monoxide, and all the 5 different data are there. So it's an interactive map. So what does it say? It says that in Great Britain, the most amount of greenhouse gas the data is after 1990. Okay, 1990 to till today they are doing. So it has been seen that from 1990 till today, the most amount of greenhouse gas that produced by Great Britain is due to industrialization. Simple. In comparison, it will be very distinct to see. In Iceland, it was much lower all these years. But just after 2000, there was a huge peak. I do not know whether you can able to see it or not. After 2000, after the year 2000, there was a rapid increase in greenhouse gas production in Iceland. Why is this so? Because the country, if you like see the industrialization of Iceland, you see that from 2020 onwards, they have opened up multiple different policies and they have set up multiple different industries also in their country. Previously, there was a net importer. The country was net importer. Okay, so it is clearly shown that greenhouse gas emission is directly proportional to industrialization, no doubt about it, isn't it? It is just an interactive real-time. आज क्या हो रहा है आपको दिखेगा. Now the problem here is the same is true for wastewater. So in this small discussion, we wanted to that industrialization leads to a lot of wastewater. So what is the solution for that? So I'll now go and okay, Asif sir. Now I'll start once again from my end. So yeah. So what is What are the solutions in this regard? That is very important as a structural engineer, isn't it? Just okay. Okay. So what are the options we left? Okay. So simulation 1 was done. So simulation lies in sustainable practices leading to technological developments in decarbonization. The topic Professor Asif has proposed. Excellent topic. And what will be the ultimate goal? The ultimate goal should be replacing the fossil fuel. This It's a long-term goal, but that is the ultimate goal. And it's this thing also now. Today we can also this thing, isn't it? Tesla is making like 10 times more profit than Ford Motors, isn't it? So it is like evident. Then subsequently recharging the groundwater level. These are the long-term goals, but these should be met. Subsequently, what? Replacing or repairing the ozone hole. Okay. So these are the three most important goals that today's sustainable development looks for. Now, how do we achieve it? Now, achieving this by hello.
Sorry, the screen is not visible.
Okay.
Can you share once?
Yes. Oh. Still now it is not visible, sir. Okay, I will then close it. No, from your end, if it is not visible, then it will not be. So what I will do is, I'll close it and once again.
I have stopped from my end.
Okay. Just give me 1 minute, sir.
Stop once and then again do it. Repeat.
Yeah. That could be good. Okay. Now my screen is shared, right, sir?
Shared.
Shared, no?
Correct.
So what exactly happened is, so what is the use case scenario that we will also discuss? Is it possible to get a net zero emission? Emission in all terms, not only greenhouse, but in terms of what we call, okay. Is it possible that, okay. So this slide, you can see, sir, the slide is in this direction. A major step taken by the industry and the scientific fraternity is the development and nurturing. This is very important.
Visible.
Yeah. This is very important. Development and nurturing of green building. Okay. So as a structural engineer or civil engineer, all of you participants as well, when we talk about green building, what do we think that okay, this green building must be having some solar panels, and subsequently they would also have no requirement for AC, means room heaters, because they'll preserve the sunlight and this and that. No, we are going to the next possible scenario, which is a literally green building. Okay, literally green. That also not a building where a lot of rooftop, this thing is there, this thing what you call forest is there, also not that. So we are talking about this. Okay. Now this is, I was fortunate to have a visit also in this place. This is in Hamburg, Germany, where a very big company has made it a point that they make a building which is literally green, even in color. Now, from where this color comes? This comes from a living organism. Now, what this living organism does is it's like putting this parts in the puzzle. The puzzle is there will be a building and it will generate a lot of waste, including carbon dioxide, isn't it? For example, let's say that it is not an industrial building. It is a simple business place. People come and stay here. Even though it will produce a lot of waste. Now, what would happen if we have the capacity to recycle all the waste it produces and use that waste to produce energy instead? Is it possible? It is possible, and they have made it a point. Okay. Now, this building uses some specially developed panels which will harvest these organisms, microorganisms, and they will use what? They will use carbon dioxide produced by this thing, or which is available in abundant in the atmosphere. It will also use solar, sunlight, and in return it will produce oxygen as well as multiple different types of what we call biological product. While doing so, it will also recharge the wastewater and make it clear. Make it clear in the sense like it will be completely usable without any heavy metals, without any organic, inorganic toxins, without any what you call this thing coliforms and all other things which are usually there in this thing what you call municipal waste. No pathogen, nothing. Okay. So is it possible? They have made it possible if you can read out all the snippets. So it is possible. I have not listing the video here. And the building's name is BIQ building, which is present in Hamburg, Germany. Okay. So I'll tell you, Germany is the most polluted country in all the Europe. It is more polluted than UK. Okay. Now, what is the system that is deployed there? Please have a look. What is the system deployed over there which makes this building, BIQ building, completely free of waste, and that also they are using the waste to produce energy. If you see it clearly, okay, so the organism which is present on the building is called microalgae. This is nothing but the green algae which is usually see if you go to a village pond and there no, you will see that the color of the pond is blue. People are taking bath there, everything is there. It looks very dirty, but some people are using it not for drinking but for bathing purposes something. Not much harm is there because this is an algae which is basically this is a particular kind of algae which they are using in this building, but these are of the same category of the green pond as you can see everywhere. In rural area it is very interesting. So what exactly it does is it uses the waste that is produced by the building or the waste they are taking from the municipal sewage. Now that sewage, this particular organism, microalgae, uses that sewage as a nutrient. You understand this? No need of any added nutrient here. Whatever sewage, because sewage, what it contains? It contains a lot of nitrogen, lot of carbon, and lot of phosphorus and many other things. So all these things, including the toxins, okay, the toxins are also there, but the organism is such that it will also accumulate the toxin and it will make the water much purer. Okay. So whatever it takes is, it takes all kinds of waste matter, okay, and recycles it into a complete usable water. At the same time, it produces organic substances, okay, organic substances which eventually produces bioethanol or biofuel, we will say. So what they have done is they have answered the age-old problem. The problem was wastewater treatment was not fundamentally viable. Why? Because it is only producing usable water. It is not producing something else. Now their system, they are not only using carbon dioxide produced by the industry or the building itself as well as the waste, not only to produce heat, it produces heat. If you see the previous one, if you can see in the leftmost panel, there are some panels you can see, green panels. These are nothing but we call it photobioreactor. Okay, now photobioreactors are nothing made up of a special kind of Pyrex glass inside which you can put a media. Media means the nutrient in which these organisms are growing. Now these organisms are autotrophic. They produce their own food and produce oxygen. You can see the oxygen bubbles also. Can you able to see? Now this whole exercise is known as metabolism. Metabolism means some reaction is going on. Now that reaction is also exothermic. So what happens is it produces a lot of energy also. Now that energy is being used to make the house warm during the winter. Okay. So this is the the deployment of the thing which they have deployed in this particular building. We will have with us 3 different use case scenario which is much celebrated throughout the world. Literally green building. Now this is a simple snippet. What exactly is going on? The microalgae are there in the photobioreactors, PBRs. Okay. And what is the inlet? If you see the inlet pipes, no, it's very interesting. So what is the inlet thing you see? It is inletting carbon dioxide. It is inletting wastewater. All the, it is, you cannot see anything like nutrient, like some good thing, nothing. What it is taking all waste things, and what, when it is coming out, no, you please see what is coming out. Okay, you just see the, in this snippet, you just see the inside arrows and the outside arrows, and everything will be clear to you. The outside arrows are what? Electricity, oxygen, bioethanol, all these good things. Okay. Now this is a fact. They are doing it in practice. And all these years, since I am trained as a biomedical scientist, so we were doing this in lab for long. Okay. My guide did. I am doing. My students doing. So we were all did all these things in lab. Okay. They are doing it literally in a full-scale grown building. Not only once, thrice. Now this is the second one. Now this second building, I have not been there. It is in California, US. Now here, you see in the right side, there is a black color building. Can you see? The opposite side, just next to it, there is a green color building. That was the older building. It's a very long, old building, not very this thing. This building was changed into a green building completely. So there are two use cases. One, you can build the green building all from scratch. You can even make a non-green building into a green building, fully functional, operational green building in literal sense. Okay. Now here you see what are the things they have made. Here the panels have been changed. We'll also have a discussion on how the PBRs or panels will be changing. Okay. Now in this case, the panel pattern has changed, but rest of the other things are there. Okay. We'll also see the deployment. Yeah. Now this is the deployment in this particular building. Okay. Now this particular building has a name. It's a net zero building of GSA. GSA is an organization. If you Google it, you will find out. They have made this building by calling two most famous, what they call, structural engineers, two organizations. They have even received a prize. Here you see. They have received the Metropolis Magazine's Next Generation Design Prize for structural engineering in 2011. It's a long, old history. Many of you already may have been there or are already aware of it. So in this one, what has happened in Los Angeles, California, they have made a old building into a completely green building, and they have made it a point that it literally becomes green. Now see here. Here also you will see the same story. All the inlets are those things which are not needed by you anymore. Waste, municipal waste, wastewater, what else? Carbon dioxide and all such things. Okay. And if you see the outlet, okay, outward arrows, what are those? Those are oxygen, those are all good things. As you can see here, algal oil, algal biomass, you can see, no? These are the things from which bioethanol is being produced. Okay. We'll also come to that point. So, this particular this innovation, what it is doing? It is doing not only giving a solution to our previous problem. The problem was the production of huge amount of greenhouse gases, including carbon dioxide, at the same time production of wastewater. Now this building, what they are doing? They are not only removing the waste and recycling the waste, they are also making use of it in a significant way. They are producing biogas, and therefore the dependence on electricity is reduced. They are even producing electricity and putting it back into the grid. So it's a very interesting thing that is going on there. Now this is the third scenario. Now here what happens? It is when next level kahi hai. In this one, what they are doing is they are not only they are optimizing a system so that they are accumulating more and more waste. Okay. Now in previous two buildings, there was a limit for which the magnitude of waste each building can handle. Okay. Now here what they have made sure is they have made sure that they will be using more and more every day. They will increase their capacity, and they are doing it by an excellent design of a carbon dioxide scrubber. Okay, carbon dioxide scrubber means it will act like an eraser, and it will erase all over the carbon footprints, whatever they are in the atmosphere. How they will do it? They have designed a particular kind of PBR or photobioreactor, which is in somehow direct contact with the carbon dioxide which is present in the environment and absorbs a huge amount of carbon dioxide every time. So we'll also do a little simulation where we'll see if a full-scale functional bioreactor is there which will remove carbon dioxide and what is the extent of carbon dioxide that can be removed. Okay, we'll also have a discussion. Coordinator sir, am I visible and audible?
Visible sir, audible.
Okay.
Yes sir.
So here what is happening? Okay, so here what is happening? The building is called yes, Green Loop Towers in Chicago, Illinois. Here they have made a building where they have deployed a carbon dioxide scrubber which is in direct contact with a microalgae or the living organism that I have told you. This organism, what it does is it gets more and more carbon dioxide and therefore it builds more and more carbonated chemicals due to its inherent capabilities, catalytic capabilities, and subsequently it builds up a huge amount of biomass which ultimately produces a lot of biodiesel. We'll come to that point. Okay, this is the deployment of the system. Okay. Now here what they have done, again the same thing would happen if you can see it properly. They will have the inlet for carbon dioxide and all the waste that this building or the associated areas are producing, and the outputs are very strange. Again here outputs are what? Biodiesel, bioethanol. Along with that they are producing significant amount of energy, electricity, biogas and all such things. Okay. So these are the three use case scenarios. The problem is there are some problem also. We'll come to that bottleneck also. Why it is not? It is used case scenario. It has been proven technically by peer reviewers and all such things that whether it is completely feasible or not. But still, I'm telling you a story of 2011, much before the pandemic. So till now, why it is not that everywhere we can see this kind of build? So there must be some reason behind it. No, so we'll come to those things. Now this is the organism we were talking about. This is the microalgae. These are nothing but small plants of small trees which are so small that you cannot even see it in a single cell. Okay, when they come together makes a colony, then you can able to see it. Okay, we are working on with this particular thing for a long period of time. So these are the different photobioreactors. Photobioreactors are nothing but glass panels inside which you put the wastewater and cultivate this particular microorganism. Now it sounds very easy, but to achieve it is very difficult because a lot of R&D is to be done. So what are the different types of PBR? You can see the construction is very easy. There is no big innovation taking place. Since the building was round, the PBRs are round. Where the buildings are with long panels, the long panels are there. As you can see here, three different buildings, three types of PBR. Okay. Now this is the fundamental unit through which the whole building is made up. See, now this is the most generalized and layman type representation of these, the gist of this all three discussions. That if you have an industry and if you produce carbon dioxide, there is no harm. If you produce wastewater, no harm, because we are having a green sustainable solution in which we will add all the waste. It will ultimately benefit all. It will not only produce biogas, it will also produce electricity. It will produce heat that you can use for different ways. Okay, by putting different protocols and this thing. If you are a temperate region country, then you use it for room heating. If you are a country like India, you use it for production of steam and subsequently do the need. Isn't it? It can even produce cattle feed. There are multiple things where optimization is needed. Okay. So why this is not why we cannot see a literal green building everywhere? We can see even in my house also I have deployed solar panels by and there was a government scheme where 20% discounts were available and subsequently many. In Bangalore, when I was a student, I have seen most of the houses at that point of time, like 15-20 years back, people were deploying this. But why not a green building? What is the fundamental problem there? We will come to this point. Now we will talk about the good things first. Now here what happens? This production of biofuel will be there, the production of drugs, cosmetics, many things are possible from this particular algae. If you can grow it in a nice way, you can do wonders with this. And why it is also interesting is the whole process is very economical. You need not to put a lot of high energy compound. It do not have any specific, it does have some specific requirement, but it is not very highly costly because you are mainly giving wastewater. Okay. So multiple different benefits are there. Now what are its food? Its foods are basically this organic waste. Okay, until and unless it's organic, it's good. Organic doesn't mean that minerals may not be there. Minerals are also organic, isn't it? Iron should be there, phosphorus should be there. So these are inorganic, but these are compounded in organic stuff. Okay. Then there are some crude glycerol, which are waste from food industry. Then what else? Cosmetic industry and all such things. Huge amount of glycerol is being present in the sewage. If you check in Bangalore or in any area, the sewage will contain some amount of glycerol. Then subsequently alternate saccharides, that means alternate simple carbohydrates. Then hydrophobic substrates, pure oil, used oil, and all such things will be done. Okay. Now these are the waste. This is the character of any common sewage. You go to any city, you pick the sewage, analyze it, do a HPLC analysis, and you will see all these things are there. Okay. So what is fundamentally off? The fundamental off thing is, okay, now this is again a good scenario that you are using the groundwater, you are polluting it. If you add this living organism into the system, you incorporate it in such a way like this green building, eventually you end up with pure water. You can even recharge your groundwater levels. Okay, now these are the possibilities. But there are some technical problems. Okay, so once again we will see here. So you are putting what? Carbon dioxide. You are putting what? Wastewater, and ultimately you are getting what? You are getting treated usable water, oxygen, and usable byproducts. Okay, like biofuel. Okay, all these things you are getting. But there are some problems. Okay. Achha, before going to this, as I have said, that it will also produce some bioproducts. So we will also do a little simulation or something like this. The previous demo, we will have a demo with a real-time analytical tool, which will give us an idea if we use biofuel instead of diesel or biodiesel instead of diesel, what will be the impact on the environment? Because Professor Asif's topic is what? Decarbonization. So can it ultimately lead to decarbonization? That is also an important topic of discussion. So we'll also have a small a demo where we'll able to calculate the amount of carbon dioxide that will be saved if we use bioethanol or biodiesel. Now this biodiesel or bioethanol will be produced from where? From these type of green buildings. Okay. So before coming to the problems, we will discuss these things also. So we'll go for the simulation 2. Asif sir, would you please play the second simulation? Yeah. By just sharing with you.
Just a second.
आप सर मोबाइल पे ही चला दीजिए ताकि साउंड भी ठीक से रहे, डेस्कटॉप में मत।
मोबाइल चल रहा है। अपना स्टॉप कर दीजिए।
हाँ।
Is it visible now?
Yes.
I'm just playing.
Okay. Now this is the simulation toolbox in which there are 5 different types of supplementation with diesel. So what exactly happens is our combustion systems, which is there in your automobile, it is not ready for a complete 100% biodiesel. So what exactly Brazil people are doing, multiple countries in India, what they are doing is they are putting a blend. Okay, now there are 5 different types of blend. One is B2, then B20, then B50, then B100. Now what is this blend? Blends are, for example, B2. B2 is a blend where 2% out of 100 ml, 98 ml is conventional diesel and 2% only is biodiesel. Okay, so if we use, this is a very nice tool which gives us exact amount of carbon dioxide if we use a particular kind of blend along with a regular diesel. Now, if we achieve the ultimate goal of supplementing complete diesel engine with our biodiesel, then what would happen? That also you can quantify. And it has given a clear indication. It's a highly acclaimed tool, and everywhere environmental engineers are using it, even for their study as well as research. So what exactly happens is, I have tried to make a video so that I need not to put the whole exercise all together with all of you. Here what exactly happening is, they are also quantifying the amount of carbon dioxide that can be saved. Instead of using a regular diesel, if we even supplement 2% with 2% biodiesel, the impact is huge. In millions of tons, carbon dioxide can be saved. The idea of this particular demo was. So overall, what is the take home scenario? The scenario is our need for growth will not come to an end, and therefore the amount of wastewater produced and the amount of greenhouse gases produced cannot be stopped all on a sudden. So what is the option left with us? We have to recycle all these waste into a usable form. Okay, and we also have to do it in such a way that there is an industrial benefit. Okay, so if we want to replace our conventional wastewater treatment plants with a smart plant, what we need to have? Okay, we need to deploy these microorganisms. We have to do a lot of research with all these microorganisms. Why a particular kind of strain is only available, and if a company is there which monopolizes this particular microorganism, then what would happen? We should have some sufficient. Okay, sir. Abhi ye kar dijiye, unshare kar. Okay. So what would happen? What would happen if we? Okay. If a particular the company comes and patents this particular organism or this kind of organism, what would happen? So there are multiple different things are there. The main thing is we need to make it so sustainable and so easy to deploy that it becomes a reality very soon. Okay, we'll come to this point now. So, okay. So we cannot stop the development, isn't it? So we need to have an idea that what should be done for this, how we will deploy these innovative solutions in our existing cities. Okay. So this is a snippet where we see the method of producing that biofuel through these organisms by using wastewater. Now this second snippet is again very interesting. See here, what we are putting water, nutrient, light, carbon dioxide and all such things. Okay. Now these nutrients are nothing but wastewater. Just one more. Oh, okay. So here we are not putting good usable water. We are putting wastewater because wastewater contains all these nutrients that is needed by this particular organism. Okay, and then this is again a use case scenario which was being published recently during the pandemic 2020, where a particular group of scientists, I mentioned their name, what they have done is they have used activated sludge to produce biofuel. Okay, not only that, they have calculated the octane number of that biofuel also. Okay, they have not made this thing. They have done everything so that there is enough use case scenario where it clearly shows that from these waste we can make these fuels, and even we can make use of it. Okay, there is no fossil fuel that has been used here. Everything came from a wastewater treatment plant. This is the whole scenario which is given. Despite of all this, what is the problem? The problem is there are several scientific bottlenecks. Okay, so one such bottleneck is this. Okay, where we are working on. Okay, we are not working on the building as far. We are working on this particular organism. Okay, now in this particular organism there are four major problems. The first one is there is only some specific strains which can do this thing very rapidly at a industrial scale. All these organisms, what they do is this microalgae, because microalgae is very common. You go to any stagnant water body, you will see a layer of green organisms. Many a time it turns into some other color, but this is the microalgae we are talking about. But what is the problem? But these particular microalgae also can able to recharge the water, produce a lot of oxygen, everything is fine. But to make it into an industrially scalable business, there need to be investment in terms of R&D significantly, because we need to do these four things. One, the organisms are short living. Short living means what? Every time you have to regenerate this cell. Every time you have to add this cell to the system, and therefore the cost becomes prohibitive. Green building to hai, lekin green building tum India mein nahi khare kar sakte. If at all you can do it, you will do it in a small scale. You cannot deploy it everywhere, isn't it? And one more thing, special nutrient requirement. There are some special requirements which are still not met from the wastewater. Okay, wastewater का problem नहीं है, उसमें added nutrient add करना पड़ता है. These are trace elements, molybdenum, okay, then cesium, then selenium. So these things are specific and so costly that the whole system becomes prohibitive. So is there an option that we can remove these bottlenecks? So people are working on it throughout the world. Then there are regular strain improvement. Organism जो है उसका mutation हो जाता है. So mutation is a very common language these days. Mutation means what? The character becomes changed. Previously it was a good student, now it has become a bad student. The environment is such that eventually it becomes a bad student. So we have to make some arrangement so that the good student remains good student always. So that is a challenge, and all these things need to a lot of R&D. Okay, which small these are the steps that we do in our lab. We identify the organism from natural resources, and then try to optimize the system. We are doing it in a very small scale, but we are working in this particular direction. There are multiple different distinct limitations of our skill, limitations of funds, and so many. Therefore, but our optimum goal is that. Now, how the strain improvement process is going on, I'll just give you one more demonstration. You may not be very distinct to this, but it will be unjustified if I do not share this particular thing to all of you. Again, coordinator sir, I would request you to share your screen and do this thing. Is this possible, sir? You can do it from your desktop or laptop, but it cannot be done from the mobile. Coordinator sir, am I audible?
Sorry, I was okay.
No problem. Yes. Yes. So, sir, I would request you to. Yeah. For the simulation 3, no, I request you to again share your screen, sir. And the link that we provided,
I think
I have shared with you in the email one toolbox as well as two data.
Okay. Shall I play the? Shall I open this software or the link?
Yes. No.
Shall I open the software directly?
Okay. Yes. So in this one is just a small demo. So it will give us an idea.
So you stop sharing your.
Yes. So here we'll just have a demo that how this interdisciplinary work is going on. Okay, our goal mainly is to make it very convenient to build literally green buildings everywhere with your help, with the help from structural engineers like you. And while doing so,
is it visible?
Yes, it is visible. Yes, it is visible, sir. I think you have not shared your whole screen. Sir, it will be great if you can share your full computer screen, not a particular window.
1 minute.
So, what is the ultimate goal? The ultimate goal is to reduce cost, isn't it? R&D क्यों करते हैं? R&D इसलिए ताकि cost कमाया जा सके. So, how exactly we will do that? This thing. Cost means what? Because you need to find a particular strain, which is not very easy, isn't it? And if at all you have found that strain, which can give you constant supply of oxygen and then all of the rest of the other things, including biogas and biofuel, your strain will instantly die. Every time you have to go to the shop and purchase. If some company comes with a monopoly, then what would happen? Again, same thing will be there. आज क्या है? आज पेट्रोल डीजल का क्यों है? Because it is limited in supply, isn't it? So once that particular strain also becomes limited in supply, what will be the thing? The scenario will once again come back to this scenario. Only that global warming will be slower, isn't it? Wastewater will be the water resources will be preserved more. But one day will come where monopoly business will start again, isn't it? So is there an option that it could be generalized? That is the ultimate goal. Let us see what exactly we will be doing.
I think
so here there are two organisms. Okay, one organism is highly stable. Okay, so we will first see why this particular organism is stable. Okay, the organism that we are working on. Organism means what? A macroalgae which have the capability to recycle wastewater. Okay, which ultimately you can put it into a green building, into these photobioreactors or the window panels. Okay. So, sir, I'll request you to go to the file menu. Yeah, file menu, and then open.
L1.
Now you can this thing open the first. Okay. Now this is the skeleton of the organism. Okay. All organisms are made up of skeleton. Now this is the skeleton of the organism. Now what we will do is we will deploy atoms on it. Okay. So this two-dimensional structure becomes a three-dimensional organism. Okay. So sir, now we will go to once again. We will go to display menu. Yeah. Now we will go to molecular surface. Bottom. It will take a little time, and now it will deploy all the. Now all the atoms are there. Now, what exactly happens according to the laws of thermodynamics? What it says is each atom is defined or is classified with its inherent delta G content. Now, delta G is free energy. Okay. Now, what it says that if and all free energy contents are having a threshold. Now, if in any atom the delta G content is more than the threshold, it means the atom is unstable and eventually it will die. Unstable means what? It is having a lot of energy and therefore it will disintegrate all by itself. The stability of the molecule will be low. So now what we will do is we will calculate delta G content on each and every atom present on this organism. Okay, so how we'll do that? This particular tool that we are using is a 25 MB tool, and it does excellent work for biomolecular simulation. Chemical engineers and then environmental engineers will do this. Even this thing, what you call mechanical engineers, to identify the tensile strength of a particular, what you call, metal or metal complex, or this, what you call, composite materials. Okay, now this is an excellent tool which will calculate the delta G value of each and every atom. Not only it will do this, it will also give a particular color on the basis of the delta G content. If the delta G content is beyond certain limit, it will give it a particular color. If it is within the limit, it will also give a particular color. So remember that we are studying the first organism. We have given two models or two, what you call, data files to our coordinator, and the first model we are studying. Okay, remember. So now we will go to one more this thing, which is called what? The color. So there is a color window. Very, very simple. And now you, sir, go to temperature. Yeah. Now you please click it, and it will do a little computation, and it will. Now it has become. It has given the whole organism a particular color. Okay. Now this color is blue. So usually blue means delta G value less than 0. So if delta G value is in negative magnitude, it means that the organism is stable. It will withstand the test of time, and eventually it will remain there. Not like any other organism which will instantly die. उसको temperature थोड़ा ज़्यादा हो गया, optimum के बाहर हो गया, ये मर जाएगा. It will withstand and try to acclimatize or try to, what you call, adjust itself with the changed atmosphere, or change pH, or changed ionic concentration, or changed, what you call, the amount of toxin that is present ppm. Okay, so this is a very good organism. This is a good strain that we can select. Okay, now we'll see what happens with the bad strain. Sir, now I'll request to once again close this window and once again reopen. This simulation is done. Now you can close it from, you close it, and then once again click, and then we will do the same with the second model. Okay. So due to a limitation from my side, I could not do it, and I had to depend on our coordinator, sir. Now, sir, once again go to the file menu. Yeah. Then open and select the second organism model. Yes, this is the second model, sir.
I think just a minute, I'll just see. You had two.
No problem.
But both are L1 model.
No, name is L1 only. L1
I think I'm
just make it
ASN. I am opening ASN 45 GLY.
Acha. Okay. So we'll go to again the same way. This is the skeleton. We'll add the atoms. We'll go to display and do the molecular chart. Okay. So up to this much, it will look exactly the same. There is no harm. Okay. Now we'll go to again color and then put here temperature. Now we'll see what happens. Which this thing our coordinator given us. We'll see just now. Okay, the coordinator was correct. So what happens here? It's a completely different color. Why? Because the tool has quantified the amount of free energy present on each atom. Okay. I'm simplifying it to a great extent in order to make it this thing palatable to our participants. Now here what happens? Here it is clearly showing that we are not blue. We are blue at any small terminal part. Means only this much will remain if there are rapid change in the environment. Which kind of change? Ionic concentration of change. All on a sudden, bicarbonate ion is increased. Okay, pH has changed rapidly. Temperature has been changed due to some reason. Okay, some or the other thing has gone wrong in the environment, and this organism will die instantly. And therefore, you need once again go to the shop and bring that organism and re-enter into your system. Or you change your system completely. Means you flush out all the nutrients that was there inside your building, and then once again design the medium or the waste and then put it. So we cannot depend on this kind of organism. We need to have something which is very, very stable, can withstand certain amount of fluctuation, isn't it? Okay, so this is just a simulation where we are trying to identify much stable organism. It takes a lot time, but there is a process which can be optimized, and this particular organism can be identified. After that, we will hand it to the structural engineers who will generate the panels, and eventually we will end up with building a green building, literally green building. That is the long-term goal. Now, thank you, coordinator sir. Now I'll go once again to my this thing.
Okay, I'll just.
So, okay. So here what happens? Simulation 3 gives us an idea that this is possible. The bottleneck can be overcome. It needs a little funding from the government. This is the whole pathway, and this is not to be discussed with you. This is the genetic engineering part which needed to be done. Can you see this is a single cell. Okay. Anyway, so these are the developments that are done in our lab. We have reported this some part of the study.
Sir, sorry to disturb. Are you sharing your screen?
Okay. It is not. It's not visible. Okay. Yes. Once again, doing it from all over again. Okay. Share your screen. Sir, can you see the black thing now? Black screen of mine.
Visible.
Okay. Sorry for your inconveniences. I am subscribed to the other tool that is used for this kind of presentation. Sir, abhi dikh raha hai? Can you able to see, sir, my screen?
It's visible.
Okay. So these strain improvement simulations, and literally we are doing it in our lab within our limited means. This is the process that need not to be discussed with the structural engineer. Okay, and if you can see the single cell, you can see this is photographed in our lab only. Not in a it's a fluorescent microscope. Okay, now this is this thing, a small part of it we reported last time in a Taylor Francis group paper, and this is the previous one which is in 2019. We put it with Springers. Okay, now one more development has come. The development is sensing what is going wrong in the media. Okay, this is one more aspect of this today's discussion. Here what happens? Here there are some more development that is taking place in the this thing, what you call this municipal sewage treatment plant. What are the different developments? Okay. So this is one more development. Here we are deploying different types of sensors throughout the system so that nothing remains unpredictable. If there is a rapid change in pH, that also we can identify. If there is a rapid change in turbidity, that also we can identify in a real time basis. Not koi jayega, jaake sample laega, sample like lab laega. No, at the point of care itself. Okay, in a point of interaction itself, it will take the reading and send it to a third party server. The server will analyze and predict what would happen after like 12 hours delay. If the turbidity is developing, after 12 hours, what will be the ultimate turbidity of the whole system if everything goes okay the way it is going? And will it be alarming? If it is alarming, it will alarm the operator to make necessary adjustments. Many a times it will do the necessary adjustment all by itself. Okay. So these are some new developments that are being this thing in green building concept. This is very, very important. As I have said, that there is a rapid problem where the texture of the media changes. क्योंकि ये तो it is very this thing palpable also because it's a the municipal sewage is a dynamic thing. Okay, it is not static. There is no this thing that every time there will be seasonal change, there will be monsoon, there will be drought, there will be this, there will be that. So there will be different changes. So how to make it convenient? If we are completely dependent on a particular kind of what we call chemistry, then it's a limiting factor. How to overcome that? In order to overcome that, we have to deploy these, not only the sensors, but also a responding mechanism to it, so that whatever changes is taking place in the medium, that is the wastewater, it gets adjusted all by itself. Okay. Some the organism will do, some our smart system will do. Okay. So this is how the integration can be done. This is the computer science people this thing discussion. Okay. So here is one more snippet where whatever thing I have said just now, it will not only check the pH. Somebody will go and check the pH. No, it will check all by itself, and the buffering will also be done automatically. Okay, not that somebody will go and add disodium hydrogen phosphate. So it will be done automatically. So so that what would happen is it will eventually be this thing take care. The system will take care all by itself. Okay. And this is a use case scenario where hydrogen sulfide sensing is done very nicely. Okay, and very low cost way also. Okay. So what has happened? They have put the hydrogen sulfide sensor throughout the system, because hydrogen sulfide is something which will kill the organism. Okay, to a significant extent, but it will hamper the whole this thing what you call operation to a great extent, and therefore it needed to be tackled much more than the pH change and all other things change. If hydrogen sulfide build-up is there, the organism will eventually eliminate. Okay, so this is a system which already has been deployed, where hydrogen sulfide is monitored very stringently, and to mitigate the problems, the system responds all by itself. Okay, this is the long-term system where all the snippets are there: pH, turbidity, salinity, then all other things, the bicarbonate ion, then what else? Hydrogen sulfide and all other sensors are there and working in sync, so that no rapid change takes place in the whole system. So it is some third party, but it is not anything our work. So in that regard, we have tried to build up some intellectual property, and we have reported, and we are hopeful that it will get granted. And we are also in discussion with some industry, some companies who are already in this particular business, and food companies and wastewater management companies in our limited area only, where we are trying to monetize the small development that is taking place in our lab. Okay, we have also sent some of our development to a body which was there in IIT Mumbai, and the first round was been cleared, and we are also hoping that we will get a call from them for some more discussion on it. Okay, so these are the some things that we are interested in, where we are sincerely think that there will be some kind of development that we can contribute to the need of decarbonization. So with this note, I would conclude, and if I can answer some of your queries, I will be very happy if I can do that. Coordinator sir, over to you. if some these things are there.
I request participants to, sorry for the delay. I request participants, if you have any questions, you can.
Yes, they are having some interesting discussion.
I can post in the chat box, even. We'll see. Sir, from my side, I'll just like to ask. It's good that we have some living roofs over the roof now, which is green, which you said algae and all. Is there any disadvantage of that, like means for with respect to health?
Right now, no. There are two aspects to it. The desperate need is to deploy this thing. Okay. So in health wise, there is no this thing since you are not eating it directly. So there is as such no problem with it. Only problem is we were not able to till now optimize the whole process in such a way that we can build these green buildings every now and then. Okay. So this is the biggest problem till now, that the panels are there, people are ready to invest. There is a proven track record that most of the waste will get eliminated. It will not get back to the system again, and the building will look after itself. Whatever the people who are producing the waste, no, they'll recycle the whole waste and eventually they'll use it. And will reduce it to a great extent. That is fine. But the problem here is not with health, but with the organism. Okay, so there should be some mechanism which will reduce the probability of the damage. And one more regulatory aspect is also needed, where nobody can come and monopolize this thing. So what would happen? No, again we'll reach into the same scenario like today, isn't it? You cannot make a well and produce fossil fuel for you. No, you cannot make diesel. You have to depend on somebody. So that same thing will happen. The ultimate goal, no, will be like this: to not only design a highly optimized building, also to reduce the monopoly if it is there. Today, what is there? If you at least a solar panel gives you some autonomy on your energy, isn't it? You deploy a certain amount of, like, for example, 3 kilowatt is deployed to your house. Okay. Now, what would happen if it could be off grid, on grid? Either if you produce surplus, you can sell. Otherwise, you can use it for yourself. So some autonomy is there with solar panels, isn't it? But still, you need to depend on somebody for the solar panels. You have to maintain it. But still, it is good, isn't it? But this solution is such that it's a path-breaking thing. If it is reaches the way solar panels have reached today, that also will be a great thing. But for that, an integrative approach is needed. Structural engineers will work with biomedical scientists. Biomedical scientists will work in sync with computer people, then electronics people for IoT devices. So, if this kind of ecosystem is being built, then there is a huge scope in this particular scenario also. It sounds a little futuristic, but there will be no other option other than depending on this microalgae. So this is how I would like to. There is no such health problem.
Okay, sir. Any other participants? I think there are no questions. Shall we end, sir?
Yes, yes. If
Thank,
this thing is there.
thank you, sir, for being with us and showing interest as a research person for this and giving insight of your topic. From our end, just a minute, sir. I like to share from them. Can you stop sharing?
Yes, yes. I'll just. Yes.
Just a minute, sir. I have lost my internet.
No problem. Yes, yes. I think there is a question in the chat box. Okay, Dr. Tausif Ahmed has asked one question. What is the cost? Okay. Till now in India, I have this thing. I doubt that there are any functional, but there are multiple labs who are working on this aspect, including us. But I would rather say that most of us are in this thing, lab scale. Okay, the building is far, we have to optimize the panels also, which kind of design is there, many other things. So still we are in the lab scale only in order to minimize the cost. We have not reached the German people. I have been there in that building also. I have worked with these people in a limited scope. I have not able to learn many things. The Hamburg ones I have said no, 2012, long back. But till now there has been no much the cost of construction in terms of the glass panels and all. It will not be much. But once you deploy the whole working system, the main cost would be optimization. You have to deploy the devices also for sensor and multiple different other layers are also there in terms of construction as well as optimizing that strain. The strain is not yet optimized from India also. That is European strain. Means temperate region जहाँ पे temperature थोड़ा कम है, हमारा इंडिया का माफिक नहीं है. In those areas, that particular strain that is going on in Germany, even in USA, but in India, the strain yet is not yet developed. So it will take a little more time because, as you know, that there are many limitations. Okay. Structural engineers' contribution is huge. But it's not only huge. It's the most of it. The more the building is being constructed by structural engineer, they are the one who will tell us that how maximum amount of sunlight can be utilized and maximum amount of carbon dioxide can be scrapped into the medium. The structural engineers work is the more than us. once we have standardized the medium and standardized the organism, then it's all your work. I would say. Thank you for asking 2-3 questions. Thanks. Thank you. Okay. Thank you, Asif sir, for this nice certificate.
Sir, thank you very much, sir, for being the resource person for this. From our end, we like to present e-certificate to you. Please accept this e-certificate, and we'll be in touch with you for future. Thank you. Thank you very much.
Thanks a lot, sir. Thanks a lot. It's been really wonderful. Thanks.
Participant, I'll be sharing the this one link. Just a minute.